Welcome to this explainer. Look, today we're doing something a little different. We are completely transforming your mindset. We're stepping right out of that hobbyist world of just tinkering with development boards, and we're stepping into the shoes of a professional architect building production-grade systems using the STM32F407 VGT6. If you've ever wanted to know how real industrial electronics are designed from the bare silicon all the way up, you are in exactly the right place.
Here is our roadmap for today. We'll be looking inside the STM32 brain, decoding datasheets, designing pro schematics, power and PCBs, firmware and debugging, and finally, a real industry project walkthrough. We're going to be zooming out, starting at the microscopic silicon level and progressively panning all the way out to a real-world application.
All right, let's dive right into Section 1, inside the STM32 brain. Before we even think about writing a single line of code, we've got to get crystal clear on what an MCU actually is. Think about your laptop CPU for a second. It's basically just a management brain, right? It needs an external hard drive, RAM sticks, and a massive motherboard just to function. But a microcontroller, that is a self-sufficient factory completely packed onto a single chip. It's got the management brain, the storage warehouse in the form of flash memory, your active workspace as SRAM, and the shipping docks, which we call peripherals. The whole shebang is integrated into one microscopic package. And honestly, this is exactly why the big players rely on the STM32 for serious industry-level applications. Now don't get me wrong, platforms like the Arduino or the ESP32 are absolutely fantastic for slapping together a quick prototype. But the STM32 gives you a truly robust industrial architecture. It gives you absolute deterministic control. We're talking advanced direct memory access and incredibly complex interrupt systems. Because when you're building, say, a medical device or a precision motor controller, you don't just need it to work. You need it to work flawlessly every single time under incredibly strict timing constraints. So check out the Cortex-M4's Harvard architecture here. It acts exactly like a multi-lane superhighway. You see, older chips force instructions and data into a single lane, which cause massive traffic jams. But the STM32 uses separate buses, so you can fetch data and instructions simultaneously. Combine that with the nested vectored interrupt controller handling your emergency tasks and direct memory access, which literally allows your peripherals to talk to memory without ever waking up the CPU, and you've got an absolute powerhouse of a chip.
Okay, moving right along to Section 2, Decoding Professional MCU Datasheets.
Yep, 1,000 pages. That is the sheer volume of a typical STM32 documentation package. Honestly, staring down a 1,000-page PDF is enough to make a grown engineer cry. And that is exactly why you need a professional strategy to navigate it, because otherwise you're going to be completely lost in a sea of hexadecimal codes and voltage charts. So here's a massive pitfall I see all the time. Folks mix these two documents up, but professionals know the difference. The datasheet is basically your spec sheet. It tells you the absolute hardware limits, the pinouts, the thermal thresholds. You use this when you're physically designing the circuit board. The reference manual, on the other hand, is your dictionary. That's where you find the microscopic register addresses, clock configurations, and timer setups. You use the reference manual when you are actually writing your firmware. Now, because a physical chip only has so many legs, engineers use something called pin multiplexing. It means a single pin might act as a UART communication line or a timer output or an analog input. We have to map these alternate functions incredibly carefully using the datasheet, because if we don't, we make the very painful, very expensive mistake of colliding two essential peripherals onto one single physical pin. And just like that, your brand new custom board is totally useless.
Which brings us to Section 3, Designing Pro Hardware Schematics.
Now that we've mapped our pins, we build the schematic. And this right here is where we separate the pros from the amateurs. It is way more than just drawing lines between pins. It's about the physics. It's about physically separating your noisy digital power from your super-sensitive analog power. It's about placing decoupling capacitors intimately close to the MCU so they can provide immediate bursts of current. Honestly, forgetting a simple decoupling capacitor right here is exactly why your microcontroller might just randomly reset out in the field the second it tries to switch a high-speed load.
So, picture this scenario. It plagues even veteran engineers. You check the schematic a dozen times, the logic is flawless, but the physical, custom PCB still crashes constantly. Why does this happen? Well, the answers are hidden deep in the physics of the physical board itself.
Let's pull back the curtain in Section 4, Power, Clocks, and PCBs. Look, before you go tearing apart your code, you've got to look at your power and clocks. If your low dropout voltage regulator can't handle sudden current spikes, the chip is going to experience a voltage drop and trigger a brownout reset. Or take the clocks, for example. The STM32 has an internal oscillator, sure, but it drifts wildly with temperature changes. If you need precise industrial timing, a properly routed external crystal with exactly calculated load capacitors is completely non-negotiable.
Professional PCB routing is kind of a dark art. Amateurs love to rely on autorouters, but that usually just accidentally creates massive antennas for electromagnetic interference. Professionals use strategic layer stack-ups. They know that physically separating the analog ground from the digital ground is the only way to prevent the microscopic electrical noise of high-speed digital switching from completely destroying the accuracy of your ADC readings.
Okay, Section 5, Firmware and Hardware Debugging. Your hardware is now physically perfect. So, how do we actually write the code? Well, you've got a major architectural choice to make. You can use the hardware abstraction layer, the HAL. That gives you pre-written functions for rapid development, which is amazing for getting a complex project off the ground fast. Or you can go bare metal. That means manipulating the registers directly based on that reference manual for highly optimized absolute control. Knowing whether to use a layered RTOS state machine with the HAL or raw bare metal drivers is going to dictate the entire software architecture of your product.
And when that newly minted board inevitably refuses to boot on the first try, don't panic. Just follow this triage flow. First, grab your multimeter and verify the VDD power rails. Is the chip even getting juice? Second, check your SWD detection. Can your computer even see the chip's brain? And third, probe the external crystal with an oscilloscope. Because if that crystal isn't oscillating, the heartbeat of your system is flatlined, and literally no amount of code is going to fix it.
Let's pull it all together in Section 6, Real Industry Project Walkthrough.
This right here is what a literal real-world engineering project timeline looks like. Day 1, you're diving into the datasheet to pick the exact right MCU. By week 2, you're mapping those multiplexed pins and drawing the schematic. Week 4 is all about routing ground planes to prevent EMI. Week 6, you're finally building out that RTOS firmware, and Week 8 is grabbing your multimeter and oscilloscope for hardware validation. It is a highly structured, step-by-step sequential process. You see, mastering the STM32, or honestly any complex microcontroller, isn't just about banging out some C code. It's about holistically connecting the physical physics of the hardware and the power delivery all the way to the logical flow of the software. That is the true blueprint of a systems architect.
We have covered a massive amount of ground today, from Cortex M4 bus architectures all the way to PCB ground planes. So here's my challenge to you. Open up an STM32 datasheet today and just start decoding. You've got the blueprint now, so what industrial-grade embedded system are you going to build first? Thank you so much for joining this explainer, and I will catch you in the next one.